Hello friends, I am Professor M.I. Vyas. We are studying properties of gas. We have already seen various aspects of this chapter. Today further we are going into some more aspects involved in properties of gas. Let us first check what we have studied up to in these properties of gas. In properties of gas we have seen the vapor and gas. So what is vapor? What is gas? Then we have studied the Boyle's law. We have also studied the Charles law. Then we went on to the combined gas law, where combining the Boyle's and Charles law, we come out with the characteristics gas equations, where specific heat we have seen. We have learned about the Avogadro hypothesis. We have seen gas constant, universal gas constant R. Then we have established the relationship between Cp and Cv. We have seen that particular in case of gas, where we have to consider two specific heat. One is at the constant pressure, that is Cp, and another is at constant volume, that is Cv. Then we have started the non-flow process, where there is no mass interactions across the boundary of the systems. Under this non-flow process, we have already studied the constant volume process, and we learn the constant pressure process. In constant volume process, where the volumes remain constant, in a constant pressure process, pressure remain constant. These two processes we have studied in the context of how it looks on the PV diagram. Then we have established the relationship PV and T relationship. We have find out the equations for the work done during the process. We have also seen the change in internal energy during the process. Also change in enthalpy during the process. As well as we have also find out the heat transfer equations. To understand this process thoroughly, we took one exercise for each process, so it made the concept very clear. We have applied the equations that we have derived in the theory part to find out the numerical values. Today we are going to further learn about the processes. First is the constant temperature process. First is constant temperature process. Friends, in this process, temperature remains constant. As the temperature remains constant, it is known as isothermal process. It is known as isothermal process. Let us see this process in a different way. So, we are interested for isothermal process. Isothermal process means temperature remains constant. Temperature remains constant. If we draw the process on PV diagram, how does it look? PV diagram. Suppose expansion takes place. This is at point 1. This is the process start at point 1. Expansion of the gas takes place where temperature remains constant. So the process follows in this way. This is point 2. It is expansion. So in expansion, what happened? At point, the volume is V1. Expansion takes place, so at the end of the process, volume becomes V2. And the process goes in such a way that in which temperature is constant. Friends, when temperature remains constant, you can say that P into V is constant. When temperature remains constant, you can say that PV remains constant, right? And the process on the PV diagram and the process on the PV diagram is hyperbolic. Process on the PV diagram is hyperbolic. 1 to 2 it is expansion. Suppose if it is compression, the same process means on PV diagram it starts from point 1. It starts here from point 1 and compression takes place. It goes up to here, point 2. So at the initial, the volume is V1. At the end of the process, volume is V2. Again, this temperature is constant. P into V is constant. The process is hyperbolic from 1 to 2. This is called expansion. This is here called compression, right? Friends, as the curve is hyperbolic, it is also known as hyperbolic process. It is also known as hyperbolic process. Isothermal process is also known as hyperbolic process. It is constant temperature process. Now, this temperature remains constant, so internal energy also, change of internal energy is 0. When the temperature remains constant, change of internal energy remains also 0. That means it is constant internal energy process. That means It is known as also constant internal energy process. It is constant internal energy process. So isothermal process, temperature remains constant. Temperature remains constant. It is constant temperature process. As the process curve is hyperbolic, whether it is expansion or whether it is compression, so it is known as hyperbolic process. And as the energy remains constant, it is known as constant internal energy process. It is known as constant internal energy process. Now, let us see what kind of the relationship is there. The relationship. So, let us say in first concept, relationship between pressure, volume and temperature. You are knowing very well that P1 V1 upon T1 is equal to P2 V2 upon T2. Right? Here it is constant temperature process. As temperature remains constant, T1 is equal to T2. T1 is equal to T2. When T1 is equal to T2, you can write down this as P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. This is what the relationship between P, V and T in a isothermal process, constant temperature process. Let us see the work during the cycle. Now, next, work during the process. Work during the process. Now, the work means here, work means the area below this curve. Suppose if I am interested that work during the expansion process means the area below this curve, that is during the expansion, this area. Suppose if I am interested during the compression, so this is the compression process, this is the curve and area below this curve. This. So, if you take a small portion of this area, let us say it is small dV. or here in this case the same thing. It is small dV. This is the small strip, a very small portion of this entire area having the gap, or you can say this length is dV in this case. So you can find out the whole work done below this area, that is work done W is equal to area below the curve. So that is equal to integral P dV, and the total area is running from V1 to V2, V1 to V2. For isothermal process, for isothermal process, it is very well P into V is equal to C. Pressure into volume is the constant. Therefore, P is equal to C by V. P is equal to C by V. Put this P over here. Put this P over here. So, work done integral from V1 to V2 C upon V into dV. So is equal to integration from V1 to V2. C is the constant, take out, inside it remains dV upon V, right? What is the integration of 1 upon V? 1 upon V is log V. The integration of 1 upon x dx. The integration of 1 upon x dx gives you the log x to the base E. So here, and so it is log V running from V1 to V2. So it is C into log V2 upon V1 to the base E. Log V2 upon V1 base E. You are very well known, P into V is equal to C. So is equal to P1 V1 is equal to P1 V1. Right? Similarly, you can write down P2 V2. Constant P1 V1 is equal to C. P2 V2 is equal to C. Right? So, the work done during the process W is equal to C. Instead of C, you can put P1 V1 log V2 upon V1 to the base E, right? And this equation you have to keep in the mind while solving or while finding the work in the numerical. Now, friends, it is known to us that V2 upon V1 is nothing but ratio of expansion. ratio of expansion, that is equal to R. That is equal to R. You are also knowing that from characteristics gas equations, P1 V1 is equal to mR T1, P2 V2 is equal to mR T2, right? So you can write the work done. You can also write the work done during the process is equal to W is equal to M R T1 log R to the base E is equal to M R T2 log R to the base E. This is further we have in the form of mass into R into the temperature into the ratio of expansion. We have used this R for V2 upon V1. So work done is equal to W mR T1 log R to the base E is equal to mR T2 log R to the base E. Now further, the third aspects in which we are interested is change in internal energy. Third aspects, change in internal energy. Change in internal energy you can give by the equations M into CV to T2 minus T1. This is the change in internal energy du. The small change in internal energy is M into CV T2 minus T1. But here T1 is equal to T2. T1 is equal to T2. So this terms goes to 0. This T2 minus T1 goes to 0. Hence, change in energy. Hence, change in internal energy, that is du is equal to 0. Change in internal energy du is equal to 0. So what we can conclude that in isothermal process change in internal energy is 0. So it is the constant internal energy process. It is called constant internal energy process. Now our four aspects is to look into what is happening in heat transfer. What is happening in heat transfer? So according to first law of thermodynamics, from the first law of thermodynamics, it is delta Q is equal to delta W plus du. Delta W plus du. Now here du terms is 0. Du is equal to 0. So you can say that delta Q is equal to delta W. The heat transfer is nothing but whatever the change in work done. Whatever the change in heat transfer is associated, that is, it is in change in work done, and this is equal to, you can write down that delta Q is equal to P1 V1 log V2 upon V1 to the base E you can also write, instead of P1 V1, you can write MR T1 log V2 upon V1 to the base E. Now, we have seen the relationship of PVT. We have seen in the relationship of PVT. In relationship of PVT, P1 V1 is equal to P2 V2. So from V2 upon V1, it is P1 upon P2. V2 upon V1 is equal to P2 upon P1. This you can take and put in this equation is equal to MR T1 log P1 upon P2 to the base E. This is the heat transfer. And the fifth one is change in enthalpy. Change in enthalpy, that is delta H, that is equal to H2 minus H1. So is equal to MCP T2 minus T1. MCP T2 minus T1. Now T1 is equal to T2. This is the 0. So the delta H comes out to be a 0. Delta H, total change in enthalpy delta H is equal to 0. So friends, we have studied this constant temperature process, that is called isothermal process. It is also the hyperbolic process. Constant internal energy process we have seen in the context of the relationship between PV and T, work done, heat transfer, change in internal energy, and change in enthalpy. Let us do small exercise based on this, so thoroughly we can understand this. See the data. A gas is compressed during the isothermal process at a pressure 1 bar. If the volume of gas is 0.5 meter cube at the beginning and after the process it is 0.2 meter cube. Find out the pressure at the end of the process. The gas is then heated under the constant pressure until its temperature is 75 degrees centigrade. Determine its volume and mass. Assume the compression is carried out at a constant temperature of 20 degrees centigrade and take R is equal to 287 kilojoule per kg. So let us try to solve this. Let us see the given data. Let us find out the given data. Given data. What is given in the data? Volume is given at the beginning. See, the volume is given at the beginning. V1 is 0.5 meter cube. At the end of the process, V2 is 0.2 meter cube. Compression process takes place. Compression process takes place. PV, it starts at 0.1, it ends at 0.2. At the beginning, the volume is V1, 0.5. At the end, it is 0.2 meter cube. So, it is at constant temperature process, isothermal process at pressure 1 bar. So, what? The temperature is constant, isothermal, it is given that temperature is constant. P1 is given 1 bar at the beginning. At the beginning of the process, P1 is given 1 bar. What could be the pressure at the end? Here, what could be the pressure at the end of the process? So, we have to find out here P2 is how much. So, see, P1 into V1 is equal to P2 into V2. This is known for our constant temperature process. So if you put the value 1 into 10 raised to 5, we have converted this pressure bar into Newton meter square. What we did, we converted the bar into Newton per meter square by multiplying 10 raised to 5. Volume is given 0.5 is equal to P2 into volume at the end of the process 0.2. This gives you P2 is equal to 2.5 10 raised to 5, that is equal to 2.5 bar. This is your first answer. At the end of the process, the pressure is 2.5 bar. Then the gas is heated under the constant pressure until its temperature is 75 degrees centigrade. Then the gas is heated under that process, constant pressure process. From here, it is constant pressure process. It is constant pressure process. This is the third point. 2 to 3 is the constant pressure process carried out at this pressure 2.5 bar. Carried out at this pressure 2.5 bar. As a result, it is 0.2. Somewhere around volume also increases. Volume is increases over here. We have to find out this volume. We have to find out. After this, it is the constant pressure process. And at the end of this pressure process, we have to find out what could be the volume and what could be the mass. This you have to find out for the process 2-3 constant pressure process. That is, we observed 2, 3, process 2 to 3. So, let us see that part of the problem. For this constant pressure process, you can write down what is at this V2 upon T2 is equal to V3 upon T3. Because pressure remains constant, so P2, P3s are common, will be taken out. Put this, therefore, volume is 0.2 upon T2, right? T1 is T2, it is given that T1 is equal to T2 is equal to T2, 20 degrees centigrade. This is 293 Kelvin. Compression takes place at a 20 degree constant. It is given in the data. So, this is 293 is equal to V3, and the gas is then heated under the constant pressure until its temperature is 75 degrees centigrade. So when the process goes here from 2 to 3, here 3 the temperature is given, temperature of point 3 is given 75 degrees centigrade. 75 degrees centigrade. So it is here T3 is 75 plus 273. You will get V3 is equal to 0.237 meter cube. It is V3 at the end of the process, that is at point 3. The volume is 0.237 meter cube. That is second answer. This is second answer that we have find out. Now for the mass, we are interested finding out the mass. Mass that is in this entire process, it remains constant from 1 to 2 to 3. The mass of gas undergoes the various process. Initially it is isothermal, then it is the isobaric constant pressure process. So you can apply this mass P1 V1 is equal to mRT1. P1 V1 is equal to mRT1. P1 you have with 1 into 10 raised to 5. Volume at the beginning you have with you 0.5 is equal to mass M R287. Temperature T1 at the beginning is given 293 Kelvin. 293 Kelvin. Doing this, you will get mass is equal to 0.594 kg. Mass is equal to 0.594 kg. This is your third answer. This is your third answer. So friends, what it is given in this data, let us once again, first part of the problem is constant temperature process. T remains constant. The process starts from point 1 to 2. Volume is given at point 1. Temperature is also given at point 1. Pressure is also given at point 1. Point 2, the volume is given. It is constant temperature process. We have to find out the pressure at point 2. Then after the gas further undergone the process, that is constant pressure process. So here P2 is equal to P3, constant pressure process, and it is further heated, temperature goes up somewhere around it here, so the volume V3 must be greater than volume V2, so volume increases. We find out for the constant pressure process V2 upon T2 is equal to V3 upon T3. which gives you the volume at 0.3, and P1 V1 MRT that gives you the mass for the whole process, these two process gas. So friends, here this time we have seen the two combination of this numerical problem, combination of two different processes. Initially it is the constant temperature process, isothermal process, and then it is the constant pressure process. I request you go through the books, very good books, whichever you like, as per your syllabus. You do some more problems, numerical problem based on all these process, constant volume process, constant pressure process, and constant temperature process. Next time we will go further the two process left out in these properties of gas and the numerical problem based on it. Till then, a very all the best from all of us here to all my friends. A very happy time ahead. Thank you.